Now, as we have said, the capacitors, and as we have seen, the capacitors are devices which are composed of conductors where charge is stored in these. But we have seen in the previous chapters when we talked about potential and potential energies that when charge come together, there is a potential energy actually stored in this system of charges. And evidently, therefore, when we bring charge and deploy it on conductors to form capacitors, then there is energy that is stored in the system. And now we will see how this energy builds up, and also we will find an expression for the energy there, and we will eventually see actually that this energy can be viewed as being stored in the electric field generated by the charge distribution. So let's start first with the charging process of a capacitor. So this is a diagram just considering a general capacitor. Here we are showing it as just parallel plates, and what we are doing is we are considering the charging of this capacitor. Okay, so we start with a capacitor that is uncharged, and then we connect the plates to the terminals of a battery, and then the charging process starts up. Now, what is the charging process? The charging process can be thought of as being carrying a charge plus dq, a positive charge. Now, first you start with two neutral plates. They are not charged, and you connect them to the battery. Then one of them will have negative charge appearing, the other will have positive charge appearing. So what's happening is that there is, of course, this is not literally what's happening. Okay, it's important. I mean, nobody carries these charge, but in a way, it represents, gives you an idea, or it gives you a feeling of what's going to happen. So we can think that a positive charge is carried dq, a small positive charge is carried from the negative plate, from the lower plate to the upper plate. So a lower plate will have a charge minus dq, and the upper charge will have a charge plus dq. This is to start with. And this process will continue. This process will continue doing all that. So this is, you can think of as being the charging process. Okay, start neutral, and then a negative charge, a positive charge is carrying from the lower plane to the upper plane. So you will have a positive charge, small charge up, negative small charge down, and you continue doing this in continue the charging process in small increments of charge. Of course, as charge starts to build up on the upper plane, positive charge and negative charge, an electric field starts to get generated in the area region between the plates. And therefore, carrying now a negative charge from here to here, a positive charge, sorry, from here to here, you need to do work against the electric field, because this is a positive charge. Okay, it will not go by itself from here to here. You have, because there's an electric field here, there's a force pulling it back. So you have to apply external work, a work by an external force. It's like, you know, when you lift a mass from here to here, that mass will not go by itself. You have to apply work, external work, to the system of earth mass, and this will do what? Will increase the energy, the potential energy of that system. This is exactly what's happening here. An external force, external work is needed to be done on the system of charges to raise the to move charges from the negative plate, from the lower plate, which is the negative, to the upper plate. This is something that you have to keep in mind. So there is an external energy that is being input or imported to the, in the form of work, to the system of charges. Now we continue doing this until we have a final charge plus Q, capital Q, and minus capital Q on the lower plate, and then this process stops. Now, okay, now we want to find what is the energy, the total energy that has been provided to the system of charges, or the capacitor, by the external agent that is doing work when the capacitor has been fully charged. And to do this, we go as follows. we say that at some point in the process, there has been a total charge of plus Q, which is less than the maximum charge that we want to reach on this upper plate, and the charge minus Q on this lower plate. At some point, we are there. Now, there is a potential difference between these two plates is equal Q over C. This is the general result, the general rule for any capacitor, okay? Delta V is equal Q over C, or C is equal delta V over Q. Okay, now if you want to add one more charge, to move one more charge from here to here, and this charge is dq, positive charge dq, then this means that the work that needs to be done by the external force, which is equal at the same time to the change in the du in the potential energy of the system, is equal dq times delta V. What is the potential, what is the change in the potential energy of a system when a charge moves from one point to a point? It is the charge multiplied by the potential difference between these 2 points. So I have this dq now moving from here to here, okay? And so the change in the potential energy is dq times dv. But this change in the potential energy, as we have said, is just the work done by the external force to move this charge dq from here to here, okay? So this is du, and it's at the same time dw, the infinitesimal work, which is at the same time du. Okay, I want to find what is the total work then, which is at the same time the total change in the potential energy is what? Is the integral of this. So this is the dw, q over c dq that we have just shown. And if you continue doing this, add up all these works with increasing charges, adding charges dq from 0 up to q. So this is the integral in this case. And this is an integral that can be done easily. It is integral of over q, and the result is, as you can see, this is just q squared over 2, the result of the integral, and when you take the limit, it's just q squared over 2c. So when you charge a capacitor from 0 to a final charge q, the total work done by the external force, which is at the same time the total change in the potential energy. The initial potential energy was 0, there was no charge. So this is at the same time the potential energy stored in that capacitor is q squared over 2c. And this is, what I have said. And so it's u, this is w, this is at the same time the u, the potential energy, and you can put it in different forms. And one way to see this actually is to look at this graph. Now, delta V at any point is equal Q over C. The potential difference between the plates of the capacitor when it has charge small q on it is Q over C. Now, as charge Q increases, the delta V increases. So the relation between delta V and Q on a capacitor is linear. So this is delta V. This is Q. If you plot it, you will in a linear graph. And the slope of this graph is 1 over C, which is a constant, which is the capacitance, okay? This is the meaning of capacitance anyway. So if you want to find the integral, this integral, actually, it is equal, that is, you add up, this integral is just, the area under this curve as the Q goes from 0 to capital Q. This is the area of this triangle, and the area of this triangle is just Q multiplied by delta V 1/2, which is this, which also can be written this way, which can also be written this way. Okay, so this is the total energy stored in a capacitor when it is charged of a capacitor of a given capacitance C, when it is charged to a total charge Q, or to a total, which means to a total delta V. This is the final potential difference across it. Okay, now delta V here is the final potential difference when it is fully charged. Okay, so there are different ways of doing it. As you can see, it is just total Q multiplied by the potential difference divided by 2. This is what it is equal to, and it increases with Q and delta V. So for the same Q, if the capacitor has a higher delta V, then in this case you will have a higher energy. And this applies to a capacitor of any geometry. Okay, it's not only specific to parallel plate capacitor, it applies to any capacitor. This is a very important result, and the interpretation of this as being the work done by an external force to charge it. And now what the external agent? What is this external? It's the battery. Okay, so when you charge a capacitor through the battery, this extra work, this extra energy that is imparted to the system of charges to bring them, to split them into positive and negative in a capacitor, this is depleted from the chemical energy in the battery. Okay, so this is how things work. These are important points, fundamental points that you have to understand. And as you can see, everything is linked to everything. So it has to do with the potential. Potential means we're talking about work about electric field. So everything is related to all the things that we have discussed before. Now, not only this, but we can think actually of this energy, potential energy that has been stored in the system of charges. And this applies, by the way, for any potential energy that we have discussed before. We can think of it as being stored in the field, in the electric field. Okay? So when this potential energy, when the charges come together, we have seen that there is a potential energy that's created. This energy, can we think of it as being stored in the electric field that is created by these charges? To see how this works, we apply we do the calculations for a parallel plate capacitor, because it is the one where this can be demonstrated most easily and mathematically speaking. But the result is general. It applies to any electric field actually. So think of electric field of a parallel plate capacitor. Well, this is the capacitance and this is the potential difference across that. Now the energy stored in this parallel plate capacitor when it is fully charged to a given Q and a given delta V is this. Substitute for C, this expression, and substitute for V, ED. What is ED? This is the potential difference across the plates, the plates of the parallel plate capacitor. Okay? E is the uniform electric field between the plates of the capacitor when it is fully charged, okay, to a potential V. If you arrange things, you can write this as epsilon naught over 2 E squared multiplied by this quantity. What is this quantity? This is the area of the plates multiplied by the plate separation. And this is what? It is the volume of the space between the two plates. And it is the volume where the electric field exists, because the electric field elsewhere is zero in case of parallel plates. Okay? The electric field is non-zero only on this volume. If you look at this, this says the energy is equal some quantity multiplied by a volume. And this quantity, therefore, can be interpreted as energy density. So small ue, this is an energy density multiplied by the volume. So I can write the potential energy as an energy density, which is joules per coulomb, energy per unit volume, okay, per meter cube in the SI units, multiplied by the volume. And what is this UE? This is the interesting thing. This UE depends only on the modulus of the electric field in that region. So this energy density is determined by the electric field there. And the meaning of this is that, so the energy, the potential energy, is actually an energy stored in the electric field in that region, okay? And there is an energy density, which is how many joules per meter cube are there in that volume, and this amount is governed solely by the electric field in that region. So this is the new picture. And this picture is not specific to the parallel plate capacitor. It applies to any capacitor. Not only this, it applies also to any electric field. You don't have to have a capacitor there. Whenever you have an electric field in some region, the space around that where the electric field exists, as I said before, is no more the space before the electric field exists. And here is the evidence. Now, when the electric field exists, that space has energy in it. And this energy is governed by the electric field. And the energy density, the energy per unit volume, is given by the strength of the electric field square. Now, the electric field in any region space by any given charge distribution need not to be constant. So it varies from a point to a point. So for example, for a point charge, the electric field around it drops as 1 over r square. Okay? So the energy density in this case, in other words, how many coulombs you have per cube meter in the electric field, will vary from a point to a point. And it will drop as you go away from the charge. So the energy density in that case, for example, will not be a constant. It will be a function of space also. But nevertheless, it is given by this expression, and this quantity, this UE, will be a function of R in that case. And this applies to all, to any other electric field. Let's check this point before you proceed.